Hello, thank you again. So this is the notes for today's course workshop, and they are under the U of A Data Lab GitHub under the repository Geospatial Workshops, and this is the address for these notes, or you can find them on the right. There is a menu. Still not sure. So okay, so last week, Jeff Gillen started this workshop seminar, and he talked about API um, to connect to different data sets on the internet. And since we are focusing this workshop on the next generation of data sets, we are going to do something different. Before, we had to go to every site and download some image that interests us, and then probably that image was in different formats depending on what you're trying to find, and those images can be large, in the order of hundreds of megabytes or maybe a terabyte. And then once you downloaded the image, then you started working with them. The next generation geospatial data science has to do with the new way of storing images in the internet. So like similar to what we do in Google Maps, when we're using Google Maps, we are not downloading everything. We're just downloading a section. And then if we zoom in, then another information comes down, and then we can focus on the information that's being downloaded. So cloud native formats are similar. We are always getting the information from some internet server, and we are only downloading the necessary information to work on. And sometimes all the image processing can be done online depending on what geospatial platform you're using. Okay. In this workshop, we are focusing in using Python. So it's not just click like if you're using ArcGIS or some other GIS system. Here we're going to be doing everything using an interface, programming interface, and that's going to be a Jupyter notebook, and this Jupyter notebook will be running Python on it. Okay, so depending on what is the field of interest, sometimes we are studying any phenomena on the biosphere or the hydrosphere or atmosphere or lithosphere. And we will find different types of formats. For example, we may find, for example, the raster data that we are used to it. These are just like pixels of information. And we download a section, and then we start overlaying the different layers of information on some area of interest. Or we can download vector data like lines, points, some geometrical figures. Those are going to be the vector images, and the ones that are like pixels are raster data. So for example, if I'm downloading a satellite image with some information on it, it's going to be raster. That satellite image has some resolution, and depending on the type of satellite information you're downloading, the ranges of resolution can go from a couple of meters, let's say 2.5 meters, up to maybe 30 kilometers, depending on the resolution of the grid you're working with. On the other hand, we have new sources like LiDAR data sources. These are done on mounting some sensors on airplanes or some drones, and then what we get is just 3D point clouds, and this information is just the, let's say, the light that has been reflected by the object in the surface and went back to the sensor. So we have just a cloud of points, and those are also, these are also going to be raster because they have a definite resolution. Let's say I'm downloading some data or studying some data from a drone, and the resolution of the drone is maybe 1 foot or 30 centimeters, and then I cannot go further down if the top resolution is 30 centimeters. Okay, and then so these are the types of format files, and also depending on what is the application, these files can come in different formats. You have heard about shape files. These are the vector file formats, shape files. So when people talk about vector file formats, basically you must think that there are some equations or some ways of generating geometric figures. So a shapefile is just a line or that determines some boundary on some map. So that's a shapefile. Also, you will find GeoJSON or JSON files. It's just a list of, for example, the coordinates that define some square or the coordinates that define some polygon or maybe a line or a point. When you're using Google Earth engine, Google Earth, then you may select some region of the map and then download the information for that region. And those are downloaded using the formats KML or KMC if they're compressed. The raster file formats can be these digital elevation models. So maybe you go into the site of USGS or NASA and maybe you download a digital elevation to a resolution of 9 meters, the resolution for some topographic information for, let's say, for the Catalinas, or LiDAR can be, well, will be in different format. The LiDAR information will be in LAS or LAS compressed or XYZ. So these are LiDAR point clouds. The GeoTIFF are just like images, but georeferenced. So that's why it's called GeoTIFF. TIFF is just the image format. And then you will have the COG, the cloud optimized TIFFs. And these are the ones that we will be using in this workshop. So all the images are stored in some server online, and then we just consult the server and extract the information that we need. So we just need to know what server are available and what information they are stored. And then if you have the cloud optimized point cloud, also these are compressed LiDAR files, and they are stored in some structure that we can extract information at different resolutions. So imagine that you are using Google Maps, but this is a 3-dimensional image. So this will be the cloud optimized point cloud. And then will be files that not only have, let's say, spatial information, but also time information. So you will find these multi-temporal file formats, the network common data and C files or HDF or GRIP. So these are files that store information, space and time. Okay. Okay. So if we are going to be working with Python, I don't know, you must be familiar with some basic Python, and these are the basic libraries. NumPy has to do with numerical Python. It includes all the information for doing mathematics. So for example, if you're going to compute the square root or you're going to compute a trigonometric function or something, you have to be using NumPy. Then matplotlib is the basic visualization library for Python. So everything, that was the first library, and everything else is based on matplotlib. So for example, we may have heard of Seaborn, which is another visualization library focused on statistics. but it's based on matplotlib. So you don't have to write all the details over matplotlib. It has functions that will produce some basic data or plot that can be implemented very easily. Then we have pandas. Pandas is the basic Python library for doing number crunching or number analysis. So if you have a data set, you have to clean it, you have to use pandas. If you have a data set, you want to read it, then you use pandas. If you want to operate with the different columns or rows of the data frame, you have to use pandas. And pandas can include some basic function for plotting also. The next hour, the next workshop is going to be on pandas, and Brenda is going to be talking about how to use it. And then SciPy, which is a collection of algorithms for numerical computations or numerical mathematics. And so if you want to solve a system of differential equations, or you want to do a fast Fourier transform, or you want to look for analyze some time series, then you have to use SciPy. Okay. All right, so that's general Python. Now, what if we're working with geospatial data? Okay, so we will find that there's a set of different libraries. We don't have to use every library. Depending on the task you're trying to do, it will depend on what libraries you need to combine and then start using them. For example, if you are going to be working with different types of data, maybe you have to work with an array lake. If you're going to be doing, if your task can be parallelized, then you can use Dask to do parallel computing in Python. If you want to do different, if you want to treat your data sets in different chunks, then you can use Kerchunk. And if you're trying to make your code run faster, your Python code run faster, maybe you can use Numba, which is a translation of the Python into numerical Python code. And then downloading data, you can use Pooch. PyStack is just a way to access the spatial temporal asset catalogs, also called Stack. And we will be using today some Stack server. We're going to be using a Microsoft Planet Computer, which is a Stack, the same as Amazon and other sites like USGS that have different cloud optimized data sets. And then we have Stack when we're trying to use Xarray with Dask. So if you have heard of Pandas, Xarray is an extension of Pandas to work with spatial temporal data in Dask. Then this is Xarray. And then we have Xarray Spatial, and then we have compression SAR for compressing multidimensional arrays. Okay, so those are the basic general Python libraries for geospatial data. And then if we're going to be working with raster data, then we have to probably involve GDAL, which is the geospatial data analysis library. Then we can use raster frames or raster IO to read raster data, raster stats to compute some information about your statistics. And then there is a remote sensing geographical information system library. For vector data, on the other hand, we have Fiona to read Python data sets. We have GDAL again, we have GeoMesa, we have GeoPandas, which is the equivalent or the extension of Pandas into the geospatial library. And we have PyProject. This has to do for projections. And Shapely, Shapely is just manipulating geometrical objects in geospatial. If you're going to be working specifically with point clouds or drone data. Then we have PDAL, which is a point cloud data. We have LastPy, which is just Python for working with LAS files, and NumPy. So we have here just a scheme of, these are the basic Python libraries. We have pandas, we have GeoPandas, we have Dask for parallel computing, we have Rapids for doing all the transfer of files, we have Xarrays, which is the extension of pandas into Geospatial, and some other libraries. And then there's a library called HPplot, which is just an API for doing visualization on Geospatial. So these are the visualization libraries. We have the standard Matplotlib. We have the Bokeh. Bokeh is just an interactive plotting library, open source. We have Plotly, which is an interactive plotting library, but this is commercial, and there's a free version that you can use. And if you want to have your plots interactive online, then you have to rent a server or pay an account. But you can do the same with Bokeh, and you get your own server. And also we have Data Shader, which is another library. And here you can find all the different libraries. Besides those, there's many more. So you will find Matplotlib, Bokeh, Data Shader, Folium. It works with leaflets, so has to do with maps, GeoPandas, GeoPlotlib, GeoViews, HoloViews, HPplot, IP leaflet, and Kepler GL. We don't have to know everything at this part. Just need to know how to use them. And so for that, I have some example that we're going to use. So if we open this link, it will go to a Jupyter Notebooks repository. And inside this repository, we will find several examples. These are IPYNB files, which is interactive Python notebooks or Jupyter Notebooks files. And we have some examples here. And the one that I'm going to use today is the GeoFile formats, but it's compressed because it is about 46 megabytes, and GitHub puts me a limit on what I can upload, so I have compressed. So what you can do is download this file to your computer, and then we will use Google Colab to upload this file and then replicate what I have done. So I go there. Since it's compressed, I cannot open it, so I need to download it to my computer. And then once I download it, I can uncompress it locally. And then we're going to use Google Colab to work on it. We're going to mimic the Colab Jupyter Notebook, because probably it takes about an hour to compile everything. And I'll show you what I have. Okay. So I'm now in Google Colab. I have uploaded the file. Okay. Also, you will need an additional files. Let me go back to the previous. So once you have downloaded the notebook, go back one level, and then there's going to be a GeoJSON folder, and you will find, we will use the Verifier GeoJSON, which is the information of this area of interest in California, one of the fires. So this is how GitHub is rendering the GeoJSON. But if you look at the code, the GeoJSON code is just a set of points, coordinates, and geometry. So in this case, it's just a polygon with 5 points to have a closed square, and you can preview it. Yes. Okay. You have already uncompressed that? Okay. Let's go to the next step. So, but you also need to download these GeoJSON files. Okay. That they are under this folder. Go up once. They're inside the workshops notebooks. There's a GeoJSON folder, and you need to download this verifier. And you just say download here. Okay, you download it. So you will need two files, because the Jupyter notebook has three files actually. Let's see. Go back and also download the Catalina GeoJSON, which is an area that encloses the Catalina Mountains here in Tucson. So also please download that GeoJSON. And again, if you see it, if you see the code for the GeoJSON, it's just points, geometries, and it will describe this area. So please download also the Catalina GeoJSON. So now you have two files, GeoJSON and one Jupyter Notebook file, okay? All right, so now can you please connect to Google Colab using your Gmail account? So Colab, research Google, login, and then we're just going to cancel this, and we're going to upload a Jupyter Notebook, okay? So we cancel this, and we're going to file, upload. So upload a notebook. And when the notebook you're going to upload, it's going to be the one you have downloaded and uncompressed in your local machine. Select that one or drag it there and upload it. That's going to be like 45 megs. And please tell me when you're there or if you're having any difficulties. Once you're uploading of the Jupyter Notebook finishes, then you can also upload the GeoJSON files, the Catalina and the verifier. Okay. So now I'm in Google Colab. This is my notebook. And I don't have, now remember that when you're using Google Colab, once your session finishes after 12 hours of idle, all your data except your Jupyter Notebook are lost. Okay, so I need to upload my GeoJSON. So I go here and upload my GeoJSON files. So somewhere I find them. Here are my Catalina and verifier. So I upload it. It's going to be here. And again, the Catalina. And I have one also for the U of A. Anyway, okay, so they're there. Now, I don't know exactly how much information you have in your Jupyter notebook, but some information may be missing. These are images, they're going to be there. And then we're going to see an example how to extract information from the Sentinel-2 satellite from Planetary Computer. So Planetary Computer, last week we saw planet data from Planets Labs, and the university, we as students or staff or faculty, we have access to planet data, and Jeff showed you how to use the API to extract information from planet data. Now, today we're going to extract information from Planetary Computer, which is Microsoft owned, and we're going to use different Python libraries to extract the information. So basically, we're going to use PyStack client, and we're going to use Open Data Queue, ODC Stack, Xarray, Pandas, GeoPandas, Task for parallel processing, and HPplot for visualizing. Okay. Now, when we start our session in Google Colab is just a generic tool for doing Python coding. And what we're going to do today is not very common. So there are not many users who use HoloViews or HBplot or PyStack, because we're working on geospatial data. So these are very common libraries. So we need to install those libraries in Google Colab. So I already have worked with this Jupyter notebook. So okay. So I was saying that this notebook, I ran it last night, so I have all the memory from the outputs. If you have a fresh notebook, for example, my session from last night has already expired, so I didn't have my GeoJSON files. I have uploaded it again, and whatever I ran last night, since this is a fresh session, there's no more HoloViews in my working memory, so I need to reinstall it. So when you run the cell, it will just reinstall the HoloViews, and it's doing it. And now you see a sequence of different installations, library installations. These installations are in sequence, and sometimes if you put the wrong sequence, like I'm trying to install something that depends on something that is not installed yet, so it will complain. So I have to I'll do all the pre-installations before I install a library. So this installation sequence works. So I have installed this one. Next one installed that one. It will take probably like 10 minutes in installing all the libraries, and sometimes you will get some error, and then you cross your fingers that things continue working somehow. Yes, just a good wish. Because here, for example, complain that it requires a pandas library less than 2.214, but I have 2.2, and then if you try to install an older version of Panda, something else breaks. So if something complains and you cannot fix it, look for another way of doing things. There is always some other form of doing what you want to do. There is no unique form, okay? So that library complained, so I just gave up. I tried to fix it, didn't work, so I continue installing the other libraries. And all the libraries there is a main repository, which is called PyPy, and I'll show you where is it. So this is PyPy.org, this one. This is the library for all the Python libraries or packages. So let's say you're going to look for HP plot, and then it will give you all the different parts where HP plot appears. So I select this one. Right now, this is the version 0.91. And if I want to install it, I just copy that one into the to memory, and then I go to Google Colab. But then Google Colab, I need to tell Google Colab that I want to install that library. Okay, this is on the way. Wait. Okay, so, but to communicate with the system, I need to add an exclamation point before the pip install. That's why all the commands have exclamation point pip install. So that's the way you install in Google Colab, okay? And then once I finish installing everything, something didn't work. And then, okay, so the next thing is to install or import all the libraries into a working memory. So I'm going to import HoloViews, and I'm going to denote it as HP. There's an HP extension for bokeh. I'm going to import this library from copy library, import in deep copy. I'm going to import GeoPandas as JPD, and we're going to import the API for pandas from HP plot. We're going to import pandas as PD, PyStack, Shapely, shapes, and also I'm defining some functions. We don't have to know everything. The first or the best way of learning something is starting with an example that works. And then if that example does something that is similar to what you want to do, then probably you just need to change the input data and accept whatever output the notebook gives you, and then probably you can tweak and change later. Okay, so we run the first cell. After we have installed everything, it will complain because I have not installed everything. So I will assume that I have installed everything like I did last night. And then I'm going to open from Planetary Computer. I'm going to open the API, and then I'm going to, these are the links for the different data sets that Planetary Computer have. And let's see if it opens. Yes, okay. So this is the first time. So I'm looking for, I know the answer. So I'm looking for 65. And this has to do with, no, not 65. Second, was it 68? Okay. 68. So 68, the directory 68 has all the information from Sentinel-2, level 2A. And 69 has something else. Further down, I will show you all other options you can find. So I'm looking for Sentinel. I found it, so it's 68. So I'm going to get the collection for Sentinel, and then I'm going to see what does these data sets include. So they include several bands. We have the aerosol optical thickness band. We have the band 1, which is aerosol 60 meters. The band B02 is the blue band. The B03 is the green band. B04 is the red band at 10 meters resolution. B05 is the vegetation, red H, from 1 to 20 meters. B06 is the vegetation, red H2, etc. And then we have band 08 is just near infrared. Band 09 is water vapor, and some other bands, okay? Okay, so the Sentinel-2 collection in Microsoft Planet Computer is this. So you start maybe thinking why Microsoft is so generous in storing all this amount of data online for free. The thing is that if you want to process this data and then you want to buy some AWS or some Azure computing time, well, Microsoft has the data and then it will just convince you to work over their computer, right? But that's the way things are. So they charge you by rate transfer of data. Okay, so now that I have find the collection of Sentinel-2, then I will use the Barefire GeoJSON. So if you go to the Barefire GeoJSON and here you click, you can copy the path, and that path is basically what is here. Okay, so I'm going to, the area of interest is just going to be the Barefire GeoJSON, which we already saw. It's just an area of interest in California. And then we're going to search in all the collections of Sentinel-2. We're looking for the geometry, which is the Barefire GeoJSON, and we're going to select a datetime. The Barefire happened in November 2020. So we're going to look how did the Barefire region look before on 2019. So I'm going to search for all the images from October 2019 that have less than 25% of cloud cover. And if there are more than 100, I would just say a limit, okay? So I run that one, and I think I lost the information. Okay, plan B. Plan B. Okay. Okay, so from the items that it found, these are the different images. So I have from October 27, 2019. This is the timestamp 185501, and this is the image. So I find 12 images, okay, from that collection, and then I'm going to plot. So I import hpplot, cartopy, geoviews, and I'm going to plot the area of interest. And then I'm going to open DataCube. Yes, I lost all the images, right? Okay. No worries. Let's go back to the repository of the notebooks. Where is it? Let's go back to the repository of notebooks, which is, well, not this one, which is U of A, Data Lab, GitHub, and then repos. I'm going the long way. Geospatial, then notebooks. So I'm back. So this is the place we downloaded the first Jupyter notebook, the compressed one. So one of the advantages of working with Jupyter notebooks is that you can download the Jupyter notebook, or you can export the Jupyter notebook as a PDF. So I did an export to PDF that it will have all the information from that moment. So you see, well, it's not perfect. It's just like a printout. Everything's okay. Continue. Installations. Then we import all the libraries and then got the catalog back. We found out where the Sentinel-2 pages were. These are the information of the different bands from Sentinel-2. And then we extracted the information from the GeoJSON querying the Microsoft Planet computer for Sentinel-2 for one month of images in October 12, 2019, with cloud cover less than 25. And then we found that there are 12 items. And then we're going to open data queue and yes, well time. This is the information. Let's see if I still have that information. No. Where is the information? Okay. Okay, so this is the information from the Sentinel-2 as an X-array. So it has X coordinates, Y coordinates, and some time. So it's just like a three-dimensional. This is the metadata. The Y is measured in meters, and the resolution is 10 meters. The X-axis is the same, 10 meter resolution. This is the coordinate system, EPSG 32610. And the time is just this is the, whoa. This is the time in units. Okay. And these are spatial references. I'm not going to worry about that. And then the reference system, WGS84. And then this is the time, and this is the information of the bands. So this is, imagine you have a three-dimensional cube of data in the X and Y directions. This is X direction, this is Y direction, and 6 time layers. So it's a three-dimensional cube. So that's the information, and then we're going to compute. We're going to transform the bands, the band 2, 3, and 4 into RGB, red, green, blue, and then we're going to compute. This visualization, and then we are going to do parallel computing. So we're using a Dask array. And then we compute, and this is the result. Okay, so we have transformed the bands into RGB values. And again, we have a new data cube with spatial X, Y, and time. And then we're going to compute the normalized vegetation index, NDVI. And the NDVI can be computing using the combinations of the bands 8, 4, and then so we have now the information for the NDVI. And yes, and then we're going to set up a cluster of several CPUs to work on the problem. So I'm using the free tier account from Google Colab, so I will work with whatever they give me. And then I have running a cluster, so I can do different problems in parallel. I'm going to compute the NDVI and visualization. And then this was 18 seconds. And I'm going to do the visualization compute. So now I have the information of the area of the fire for different dates. And I don't want to touch this if I break it. Yeah, okay. So the images are there. And then I'm going to do use HP plot to plot the X-array. And so this is just like a time. Yes, it has a time bar here. So I can select for different times. If I don't break it, I can select for different times to see the image, how the image has evolved in time. Okay, so there's a bar here. Since my session has expired, probably it's not working. I don't know. Okay, so if you're live, then you can see that. Then I'm going to do compute the normalized vegetation index, and I have this one. Okay, and you have the color table on the right. And this is interactive, so you can find out what's the vegetation index, and probably the burned areas have zero vegetation index. This is what? No, this is 2019. So it's still the fire hasn't happened. So this is the vegetation in some strange color table. And then I continue. Then I'm going to create an animated GIF. Failed the second time, so I'm going to skip that. And then I'm going to compute the average NDVI, and takes 321 milliseconds. And then I'm done with the cluster. So I close the cluster. And then, okay, so that's the example of how to compute the NDVI for area in California before the bear fire. The next problem is similar. Again, I'm going to use planetary computer, but I do in a different way to find out what collections does planetary computer offers me. I'm going to close this side. So planetary computer has all these different collections, the 3-depth LiDAR classification from USGS, the LiDAR cloud optimized point cloud. So this is the drones optimized, cloud optimized format. Then we have the more LiDAR. We have ALOS 3D, ALOS Forest. We have Raster. We have Copernicus. We have daily meteorological data. We have daily, annual, and monthly for Hawaii and North America, and so in Puerto Rico. So this information is already in Planet. So we just consulted the Sentinel-2 the same way you can consult any other type of data set in a single place, which is planetary computer. We have Landsat information. We have the MODIS satellites products information. We have NASA. We have NOAA's products. We have Sentinel-2, Sentinel-1, Sentinel-3, aerosols, census, USDA, croplands. So these are the different data sets from planetary computer. So we just did one example consulting the Sentinel-2. This one, we just consulted this one. So in the next example, I have 5 minutes. So we are going now to look for Landsat collections. And the Landsat, these are the Landsat collections. So we are going to use Landsat 8 C212. This one, I don't, okay. And again, now we are going to look for the Landsat, and we're going to look for April 2022, and the cloud threshold 10%, and the area of interest is Catalina Mountains. So that's the Catalina GeoJSON that you uploaded. And then we found there are 14 Landsat images. Then we're going to read them and make a map. And this image or graph shows me where is the Catalinas in the Landsat tiles. Okay, so we have several Landsat images, and the area of interest is just the thing in the red square. Okay. Okay, so now we know already what images we are going to be using, and then we're going to read the data in the bands red, green, and blue, and for the bounding box, which is the Catalinas, and we're downloading the data. So now we have an X-ray cube, and again we have XY time and 3 channels: red, green, and blue. So we're going to transform the red, green, and blue bands and then show a plot. So now we have the Catalinas. So this is the Catalina area for April 1st, 2022, at 17 hours Greenwich time. That's okay. So that's about. And some days or sometimes the image is not complete. Okay, so that was the example of doing Landsat images. Following that, there's another example for Sentinel-2. I'm not going to have time, but we are using Folium now, and we're going to be constructing again, I think the Bearfire, and now we're going to analyze images from October 19 to October 21, 2021. And we found 300 systems, and then we're going to see what was the impact of fire. So these are the different images, paths, and this is the area of interest of the fire. And then we will get eventually the NDVIs. We have the X-arrays cubes. We have the NDVIs. This is for October 2nd. And then, okay. So that's another image for the NDVI, and you can find what is the color tape. Okay, so we run out of time. Trying to run all this Jupyter Notebook from scratch, it will take you about an hour. There is a section that takes about 15 minutes, depending on the time of day, the number of users in Google. So just be aware of it. Okay. Yeah, okay. Yeah, this one. This cell will take you 14 minutes. Well, last night took me almost 15 minutes. The day before took me about 8 minutes. So this computing time is going to be take a break when you're running this. Okay, so that's my presentation for today. If you have any questions, just let me know.